My name is Nick Brown, and I'm a retired mechanical engineer. 30 years ago, while providing engineering consulting services to the Pentagon, I became involved in the field of risk analysis. During the course of this work, I derived some equations quantifying risk. Very basic yet powerful relations not found in the literature. Basic equations that could be applied to any area: financial, environmental, public safety, you name it. We live in a world of risk. Oftentimes, the most that can be said about a future adverse event are the minimum, likely, and maximum anticipated consequences, yielding a 3-point or triangular distribution. In the next 14 minutes, you'll learn how to quantify risk, how to pin it down with triangulated fire. You'll visualize risk reward with new clarity, obtaining risk estimates early and readily, just when most needed. For most applications, you won't need a computer. You won't even need a calculator. You'll be able to quickly separate the risk universe into thirds to direct your actions to minimize risks. Risk analysis begins with the identification of the sources of risk. What can go wrong? What's the probability? What are the incremental consequences? What's the risk increment product? And finally, what's the summed elemental risk? That's what risk is: probability times consequences. Risks, like uncertainty, exist in everything from microscopic to galactic scales. Risks proceed from element to component to system levels in a complex manner, typically requiring numerical solution. Commercially available computer programs enable rapid calculation of risks. However, we must always remember: garbage in, garbage out. This video will focus on a single isolated element. In addition, only one area or facet of risk will be addressed. Finally, the input consequence likelihood will be a specified triangular frequency distribution. In statistical analysis, the probability density function, herein called the frequency, describes the likelihood of future consequences of an event. Shown on the left and marked actual is the triangular frequency distribution. The minimum, likely, and maximum consequence values are designated L, A, and H respectively. The base or span of the triangle is therefore H minus L. The maximum frequency, the value at point A, equals 2 divided by the span. This area under the triangle is the probability that consequences will exceed minimum value L and is equal to 1. The probability of the consequences exceeding point B are indicated by the dark triangle area. Consequence units can be any parameter of interest: dollars, human lives, schedule months, whatever. We will temporarily adopt a convention that risk occurs in the positive direction. Later, I will present results when risk proceeds in the opposite direction. Instead of having to calculate probabilities for each case, it is convenient to normalize the frequency and consequence parameters indicated by capital letters on the right. Consequences are referred to the lower limit and divided by the span, rendering them dimensionless. Minimum and maximum consequences are therefore 0 and 1 respectively. The likely consequences are A, and the reference point is B. Maximum frequency value of 2 yields the required total triangle area of 1. The normalized triangle and the risk reference point are therefore characterized by specifying two parameters, A and B. Three frequency triangles are presented in this slide, each spanning the consequence range from 0 to 1. An extremely positively skewed triangle has A equals 0 and is indicated by the dashed lines. A symmetric triangle has A equals 0.5 and is indicated by the solid lines. The extremely negatively skewed triangle has A equals 1 and has dotted lines. Keep these triangles in mind because they will define the midpoint and bounds for probabilities and resultant risks. Two curves are indicated in this slide for the symmetric triangle. The curve for risk indicated in the positive direction is the descending cumulative probability distribution. This curve was obtained by computing the area distribution under the frequency triangle. The probability of exceeding a consequence value B is 1 at consequences equal to 0. Then it begins to decrease, reaching 0.5 at the midpoint and 0 at a consequence of 1. Also shown in this slide is the curve for risks indicated in the negative direction. This curve was obtained by subtracting the previous p-value from 1. It will be used later. In the following slides, attention will be directed to risks associated with the positive direction using the descending p-curve. Shown in this slide are three probability curves obtained by integrating the frequency triangles. The resultant probability equations are indicated and can be found in any statistics text. All curves have probability values of 1 and 0 at consequences of 0 and 1 respectively. The previously shown solid symmetric curve has a probability value of 0.5 at the consequence midpoint value of 0.5. Above the symmetric curve is the curve for the negatively skewed triangle with A equal 1. As indicated, the 50% probability occurs at a consequence value of 0.707. Below the curve for the symmetric frequency distribution is the curve for the positively skewed triangle with A equals 0. As indicated, the 50% probability occurs at a consequence value of 0.293. The probability curve for the symmetric case is shown once again in this slide. The risk that the consequences will exceed B is shown as the shaded area. The risk may therefore be calculated by integrating the probability curve over the limits from B to 1. It's a mystery why this hasn't been previously reported. This is the new stuff, the material not found in the literature. Shown are the risk equations and the risk distribution curves for the three triangles. As is to be expected, the negatively skewed triangle has the highest risks with a maximum value of 0.667 at 0 consequences. Since A equals 1, this curve was generated by the top equation. Maximum risk value for the positively skewed triangle is 0.333. With A equals 0, this curve was generated by the bottom equation. The symmetric curve was generated by using the top equation up to the consequences midpoint and the bottom equation thereafter. I've indicated both risk R and reward Q in this slide. I've chosen the symmetric triangle and set consequence value B equals 0.4 for illustrative purposes. Risk is the area under the P curve for the consequences greater than B equals 0.4. Reward Q is shown at the area above the P curve for consequences below B equals 0.4. The reason for this becomes clear when it is realized that this is equal to the area under the ascending cumulative probability distribution, the 1 minus P curve previously shown. On the left side are the risk distributions previously shown. On the right side are the reward distributions. Although they appear to be mirror images of each other, this is true only for the symmetric distribution with equal maximum values of 0.5. The negatively skewed triangle has maximum values of 0.667 and 0.333 for risk and reward respectively, while the opposite is true for the positively skewed triangle. This will become more evident in the next slide. Risk-reward ratio distributions are shown in this slide. In the smaller plot on the upper left, it can be seen that the curves approach infinity and 0 at consequences of 0 and 1, respectively. Details are provided in the plot blow-up on the lower right. As anticipated, a risk-reward ratio of 1, the crossover point is realized by the symmetric triangle at the midpoint consequence of 0.5. The corresponding crossover points are 0.333 and 0.667 for the positively skewed and negatively skewed triangles, respectively. The crossover consequence ranges for all triangular frequency distributions will thus fall in the range of 0.33 to 0.667. It should be added that this crossover range should also hold true for the vast majority of non-triangular frequency distributions. While more highly skewed distributions are certainly possible, they are both specialized and rare. The results to date have been obtained for the case where risk is viewed as exceeding consequence value B, as shown in the slide on the left. Alternatively, risk can occur when consequences are below B, as shown on the right. For this case, risk R and reward Q are indicated as starred variables with R star equals Q and Q star equals R, thus enabling the use of the previously introduced equations. The risk-reward distribution previously shown is indicated on the left. On the right is the distribution for risk in the opposite direction. Once again, only the symmetric curve is a mirrored reflection. It is hoped that risk management professionals will find the equations I've presented useful. However, for the general public, it's oftentimes not necessary to use them to arrive at risk estimates. I've included 2 example problems illustrating use of these results. Please pause the video now if you wish to study these results in detail. The first example highlights 2 points. Maximum risk is less than 2/3 triangle span, and under the triangle risk must be added to the triangle minimum to get total risk relative to 0 consequences. The second example highlights the fact that the risk to reward crossover range is in the middle third of the span. Avoid the span middle to assure risk is less than reward. 2 caveats should be added here. Triangle risks and rewards may be dwarfed by movements in either direction outside the triangle. Number 2, in addition to a specified risk datum, risks are relative to the observer, your personal risk tolerance. I've listed some of the attributes of risk and reward. These suggest that risk analysis is best left to specialists using sophisticated computer programs. This is certainly true when a lot of information is available about the system under study. A problem arises, however, when very little risk data is available. Oftentimes, it is a stretch to even come up with realistic minimum and maximum values of risk event consequences. Closed-form exact solutions, that is equations, used to be the norm before the advent of computers. Insights were gained from visualizing the effects of independent variables. Of course, there was a price to be paid. We were limited to simple models. Simple models, yes, but triangular distribution of the frequency distribution is often all that is known when risk estimates are most needed. These results, which have not previously appeared in the literature, offer a wide range of promising applications, some of which I am currently involved in. I hope that you've gained some fresh insight into the nature of risk. I thank you for watching and welcome your comments at nickongolflake@tampabay.rr.com.